Welcome back to our video module on quantum mechanics. In our previous video, we took a look at waves moving across a finite square well, and we identified the general form of the solutions. We saw that even though there was a well, there was some that were transmitted, some that were reflected, characteristic in their transmission amount based on the energy and the shape of the potential. But what happens if instead of a wave of energy E hitting a potential well, it instead hits a potential barrier of some thickness? How do we use our time-independent Schrodinger's equation to come up with solutions for this type of energy in this potential profile? Just like before, regions 1, 2, and 3, let's go ahead and make this symmetrical. So this is at location negative A, this is location positive A. And while we're at it, let's make the starting place of the potential profile V, and up here positive V naught. And just like before, we're going to isolate the second derivative, and as before, we'll identify this as a K squared to identify the forms of the solution. For regions 1 and 3, we've seen the forms that this is going to take. This is simply going to be just like what we had before, and that means psi 1 is going to be some E A e to the ikx plus B E negative ikx, and psi 3 is going to be a similar form. And here I've dropped the G because we know nothing comes in from infinity. However, in area 2, something else is going on. In area 2, V is actually greater than E, so this term's going to go negative, which means that the forms of the solutions are not going to be e to the ikx, but rather real exponential solutions. In other words, if we were to write down the form of the equation now, we end up with a positive k squared, which means that psi 2 is going to be some sort of c e to the kx, some increasing exponential, plus d e to the negative kx, some decreasing exponential. Once again, we have 3 equations with 5 unknowns. We can match our boundary conditions at A and at negative A, and we can set up ratios for transmittance and reflectance amounts. So in summary, just like we did with the finite square well, we're going to set up our finite square barrier by starting with the time-independent Schrodinger's equation, identifying what the forms of the solutions will look like. This gives us a starting point for identifying the transmittance and reflectance amounts, as well as prepares us to understand the phenomenon of tunneling. Our next steps are to identify these equations and explore the tunneling phenomenon within the context of a finite square barrier. I look forward to talking with you more about this.